Hey. Okay. You might be the only one, Adam. Can you hear me well? Okay. All right. Oh, so we have more people. Perfect. Right. So we are going to talk about thermodynamics from a slightly different angle. So I hope you enjoyed last week's webinars. The last 2 weeks. Yeah, I'll just show you my approach to thermodynamics a little bit, as much as I can. I would say thermodynamics is pretty much non-existent in the A-level program, right? The equation of the ideal gas is not really thermodynamics. Thermodynamics is about the laws of thermodynamics, so that's conservation of energy. And the second law of thermodynamics, of course, which was the first law that proves that time goes forward. That's great. So did you speak about the second law of thermodynamics last week? Okay. It's quite a fascinating law. I won't be going into the maths parts of it, just to talk a little bit about it. Right, so I've prepared some problems for you, and we'll start with problem number 3, of course. Right. So let's have a look. I'll share my screen. You should be able to see my screen. If not, let me know. Okay. Right. An ideal gas is either thermally expanded, then either chorically heated, and then isobarically returned to its original state. Draw the graphs of this process in the coordinates PV, VT, and PT. Okay. So let's have a look. We have a process. We have a cycle. So the gas changes state during the process. So an ideal gas is thermally expanded, isothermally expanded. So this is P and this is V. So we choose a starting point somewhere here. And we'll call this point 1. It is an isothermally expanded. Do you know how an isotherm looks like on the PV diagram? P equals K over V, exactly. So it's a reciprocal, yes. So and it's expanded, so it's going right. So we are following we're going right to point 2. Then it is isochorically heated. So that isochorically means that the volume stays the same. And it is heated. This tells us that the pressure goes up. So the pressure goes up. We don't know how far. Perhaps we will get a hint. And then isobarically. Okay, so the final process is isobaric, so constant pressure. That means that they meet here. So 1, 2, 3. So 1, 2, 3. Okay. Anything peculiar about this process? What can you think of anything peculiar about this process? Something to do with the net work done by the gas. It's a counterclockwise process. Well, yes, the work is being done on the gas because it's a counterclockwise process. This process has net negative work, so work done on gas. Done on gas because this is anti-clockwise. Clockwise. So it's a heat pump. Perhaps it's a heat pump. Right. Or like a pump, if you think about it, like an actual bicycle pump. You're doing work on the gas. Okay, now we need to draw the same 3 processes in the coordinates VT. VT. Double check some. VT. Okay. Okay. VT. And we start with 1. So first it's going to be an expansion. So we start with 1. Sorry, that's 1. And this is an isothermal expansion. So it will go up like this. Then it's an isocore. So constant volume. And then it's going to be an isobaric, a constant pressure. So the pressure is constant. So if V is constant, then P over T is constant. If, in other words, pressure is constant. If pressure is constant, then V over T is constant. That means V is K times T. So that means V is proportional to T. So we have to have a straight line going through the origin. Okay. So we have 1, 2, and 3. 2 and 3. Okay. Any questions? Any questions so far? And also, I would like to ask you: is this new to you? Am I doing something that you haven't done before? Just say new or not new in the chat, please. Okay, PV graphs. Okay, yeah, but you could do V against T. It's also a useful graph. So yeah, that's nice. PV and PT. Finally, the PT graph. The same process in the PT. It's a good practice. Also, did you do did you do cycles in school? Because some schools do, some schools don't. Have you done cycles in school? No. Okay. Okay, so we're going PT. So start with 1. Well, should I start somewhere here? 1. Now, isothermic expansion. Isothermic expansion, so it's along a vertical line because T is constant. And we need to decide whether we're going up or down. Are we going up or down? Who can help me? It's an expansion. It is going down because if we're expanding the gas, that means the pressure drops. So 2. 1 to 2. An isotherm. Now, then it is an isochoric process. So the volume is constant. So if V is constant, then P divided by T, then P divided by T is constant. And if P divided by constant, that means P is K times T, is a constant times T. That means it's a straight line going through the origin. And the final process is isobaric. So we can see that it's going to be like this. And this is the third point. We can draw the process. So any process can be drawn in 3 different variants. And of course, the clockwise and anti-clockwise depends on the choice of axes. And the fact that this is a clockwise process doesn't tell you anything. It's only the PV that matters. So if it's a clockwise process in PV, then it's a heat pump. If it's a if it's a backwards, it's a heat engine. Good. So that's hope that was useful. Going on to the next one. A fixed mass of air in a cylinder is under a piston. A fixed mass of air is in a cylinder under a piston. A heat is added at constant pressure. Find the work done by the gas. Okay. Well, first of all, we need to understand why is there work done. Let's have a look. So you have a piston, you have a cylinder, and a piston. And there's gas inside. Or air, to be precise. Heat is added. So heat is added. At a constant pressure. Find the work done by the gas. So how do we know that the gas does work? Can somebody tell me? Because work is only done when the volume changes. So how do we know that the volume changes in this process? Exactly. Yeah, absolutely. Because it's a constant pressure, but we're adding heat. If we're adding heat, the temperature of the gas will increase. And if we don't change the volume, the pressure will grow. And I like the FET gas laws. You can quite a nice simulation here. So you can add some gas. Air is a mixture of gases, so you can add two different types of gas. Wait for a bit until they spread out. All right, so if you heat the gas, the pressure will increase. You heat the gas, the pressure will increase. And it's quite obvious. That's what pressure does. It increases when you heat a gas. So in order to keep the gas at constant pressure, we need to allow it to expand. So have a look. If we keep the pressure constant, it's going to be 9,582. When I heat the gas will expand in order to keep constant pressure. And when I cool it down, it will contract in order to keep constant pressure. Now, keeping constant pressure is remarkably simple. Do you know how to do that? Do you know how to keep a gas at a constant pressure in this scenario? Let the piston freely move. Yes, but that's not the end of the story. Okay, how can you keep the gas at a known fixed pressure? Let's put it this way. Does the piston have to apply an equal? Exactly, the piston has to apply an equal force downwards. And what's the easiest way to achieve that? Put a known mass. Let's say 150 grams. And then the pressure is equal to mg divided by the area of the piston. Like these things need to be said sometimes because they're not obvious. And if you know the weight, you know exactly the pressure in the gas piston. Well, of course, you need the atmospheric pressure. Yes, you need to know the atmospheric pressure. but you don't even need a manometer. You don't need to connect a manometer to measure the pressure of the gas, because you know the pressure of the gas, because it's this. It's way simpler than adding a gauge here, like a pressure gauge. Okay, so that's these are the things that I found fascinating when I was learning physics. I don't know, maybe you're not like me. Okay, so we add heat, and it expands. Of course, to keep the pressure constant, it has to expand. And all right, find the work done by the gas. So we write the this first law of thermodynamics, that the heat supplied to the gas does two things. It increases the internal energy of the gas, plus it allows the gas to do work. So this is the work done by the gas. So this is conservation of energy. And yeah, so this is quite straightforward. Second. Apologies. Okay. Yeah. Right. The initially the gas is the gas is okay. The initial gas has pressure 1 and volume V1. At the end, it's pressure P2 and volume V2. We know that it is an isobaric process. That means P1 is equal to P2. And we can say that the work done is P1 multiplied by V2 minus V1. This is the work done by the gas. In other words, it's P1 delta V. All right. But we know from the gas law that P1 V1 is equal to nR T1, and P1 V2 is equal nR T2. In other words, this can be rewritten as P1, this can be rewritten as nR T2 minus nR T1, or in other words, nR delta T. R delta. Okay. And we know that in an isobaric process, the amount of heat supplied to the gas is the mass of the gas multiplied by the specific heat capacity at constant pressure, Cp, delta T. Now, this is slightly different from the Cp in the assignment, because Cp in the assignment is not specific heat capacity, is the molar heat capacity. So here, let's call it asterisk C asterisks P, specific heat capacity. Do you understand the difference between specific heat capacity and molar heat capacity? Yeah, okay, good. Right, and here we are. Therefore, so pressure 1 delta V is equal to so the work done, which is equal to NR delta T, and this, on the other hand, is equal to Q over MC star. So NR delta T over MC P star times Q. RQ MCP star. Okay, and then we can say, well, the number of moles of the gas, is equal to the mass of the gas divided by the molar mass of the gas. Therefore, this can be written as MRQ divided by mu, the molar mass, MCP star. Okay, and therefore this can be written as RQ over the molar mass CP star. So it's 8.31 times Q, which is 10 kilojoule, 10 to the power 4. The molar mass is 0.029 because it has to be in kilograms per mole, not grams, and multiplied by Cp, which is 10 to the 3. So that's 10, 3, so 8.31. 8.31 times 10 divided by 0.029 gives us 2.87 kilojoules. This is the work done by the gas. It's quite a lot if you think about it. But then again, a lot of heat is supplied to the gas. A lot of heat is supplied to the gas, and a lot of work is done by the gas. And yeah, so the change in internal energy, Q work. So wonder if there's something we can do here. We know that this, let's look into this. I haven't done this, but I think we'll get places here. So we know the amount of heat supplied to the gas is 10 kilojoules. And we know that the amount of work done by the gas is 2.87 kilojoules. So this tells me that the change in the internal energy of the gas is 7.13. Yeah, 7.13. So it should be 7.13. So let's double check. So the change in U. So what is that? Well, that is the this is change in U. That is the nRT. nRT. This is the delta T, and because it's a diatomic gas, so it's supposed to be, oh, that would be at constant volume. Oh yeah, that makes sense. And it's going to be 5/2. 5/2 nR delta T. But do we know delta T? Oh, we don't know delta T. Sorry. This is therefore no. But we can work out delta T. We can work out delta T from here because we know that this is 7.13. The DU is 7.13 kilojoules. So we can work out delta T from here. Okay, I'll leave this to you and experiment with this. Okay. The next thing I'd like to do is talk about the Carnot cycle. Carnot cycle is a special type of cycle where the special type of cycle where the gas, so the efficiency of the cycle is a maximum. So with given temperatures of the hot body and the cold body, or heat source and heat sink, however you really like to call it, the efficiency is a maximum. Okay. So it says it gives out 7% of heat of received heat of the received heat to the sink. So assume the gas receives Q1 of heat. So it gives off 0.7 Q1 of heat. So using the first law of thermodynamics, in a cyclic process, that means du is 0. That means So U du is, well, simply means that dq is equal to du plus dw. So because in a cyclic process, the total change in internal energy is 0. Okay. In other words, we can say that Q1 minus 0.7 Q1, that's the amount of heat inserted, the amount of heat. So for the whole cycle is equal to the work done. In other words, the work done is 0.3 Q1. So the efficiency is the amount of work done divided by eta, is the amount of work done divided by the total heat supplied. In other words, that is 0.3 Q1 divided by Q1, which is 0.3. And because if it's a Carnot cycle, it's a Carnot cycle, the efficiency is 1 minus T2 over T1. And we know the efficiency is 0.3, therefore 0.3 equals 1 minus T2 over T1. And therefore T2 over T1 is 0.7. T1 is okay, so we know T1. So T2 is 0.7 times T1, which is 0.7 times 400, which is 280 Kelvin. That's the temperature of the cold of the heat sink. Okay, any questions? Any questions here? Anything you'd like to know? This, I want to do question 1 and 2. They are quite mathsy. And so what I want to do is talk to you a little bit about the second law of thermodynamics. So have you heard about the second law of thermodynamics? What do you know about the second law of thermodynamics? Absolutely. Entropy always increases in a closed system. Or in other words, the entropy, the total entropy will always increase. Right? So even if you have even locally, the entropy can decrease, but globally, the entropy always increases. And this doesn't just apply to a gas. So entropy is a measure of disorder. Entropy is a measure of disorder. Entropy. So a few words about the second law. Entropy always increases. So entropy is a measure of disorder. Is a measure of disorder. Basically, it's a measure of how chaotically the particles are arranged in a system, or how the particles behave. But this could be applied to anything. For example, if I tidy my room, I increase the amount of order. I reduce the entropy of my room. But if I leave it and don't touch my room, it will get disordered. So the entropy increases. So natural entropy increasing is a very natural process. You know this. If you tidy your room becomes disordered all the time, always. So how come? But then if I tidy my room, why is the entropy increasing? Why am I allowed to increase entropy reduce entropy in my room? Because my claim that entropy always increases, entropy in the universe always increases, how come when I tidy my room, entropy increases? You did work to tidy your room, increase entropy more. Decrease the room beyond tidy. I've done work to produce converted to heat. Absolutely. Yes, I've done work. To tidy my room. It does increase the randomness of the air around me. Absolutely. So yeah, you have very good understanding of Newton's second law. Did you study it yourself, or was it something covered in the webinars? Okay. Yeah, so you're quite familiar with it, and that's really great. That's really great to hear, because normally you study it at university. And I don't know, I was so fascinated by entropy. Like if you build a sandcastle, on the beach, it will get destroyed. Yeah, there's a wonderful video by Brian Cox about this. If you build a sandcastle, oh, it will inevitably become a pile of sand. So anything beautiful will become just a sand dune. So, wrong scale, but you get the point. if you build a beautiful sandcastle, it will inevitably become a sand dune, because this is a low entropy, and this is high entropy. Low entropy, and this is high entropy. Now, there's nothing fundamentally it's not prohibited by physics for the wind to pick up sand from a sand dune and assemble it into a sandcastle. The wind certainly has enough energy to pick up the sand and move it, because the wind can carry the Saharan sand to the Amazon River. Can you imagine that? So the wind can pick up sand from Sahara and deposit it in the Amazon rainforest. So the wind has enough energy to do that, but it doesn't do that. And the reason why it doesn't do that, because of probability. Basically, there's only one way in which the particles can be arranged in a sandcastle. Well, assume there's only one way. Of course, if we change the particles around, there's one arrangement. And here you have millions of arrangements, billions, trillions, lots of arrangements. So there's only one arrangement of the particles that makes a sandcastle. And there are millions of different arrangements of sand particles that make a sand dune. There is a chance that the wind will pick up the sand and deposit it and create a sandcastle. It's just the chances of this are minuscule. You have very low chance of it going from there to there. It's not impossible, it's just very unlikely. So this process is very likely, and this process is very unlikely. So it is very unlikely that something would happen to your sand and it will go into from high entropy to low entropy, because there are 500 billion ways of how you can make a sand dune, and only one way how you can make a sandcastle. Of course, there's not one. You got the point. Yes, and this determines the flow of time. This was the first law that said time does not go backwards. Time can only go forwards in the direction the entropy increases. Now, there's a problem with that, because one might argue that wait a second, but what is the definition of time then? If we define time as the direction in which the entropy increases, then we're stuck in a loop. What is forwards? Forwards is the direction of high entropy, and what is the direction of high entropy is time forwards. So it's a loop here. Anyways, going back to the two questions, question 1 and 2, they are quite mathematical. I don't know if you'll enjoy them, but this just shows you the kind of approach. This is probably going to be university. It's not university level material, but it's probably the university level approach. the good thing about it is just that it's a bunch of equations which you can solve. So let's have a look. An ideal gas is a 1 mole of ideal gas, and it performs a cycle consisting of 2 isobars and 2 isochores. All right, so this is PV. Isobars, so start here. Let's label this. Let's call it 1. Then isobar, so it's a work done by the gas. That means it's a clockwise process. So go 1, 2, 3, 4. Okay. The work done by the gas per cycle is 200 joules. That means that this area, so let's call this P1, let's call it P2, let's call it V1, and let's call this V3, because, yeah, we can't call it V2. V2 is here. V2 is equal to V1, and V3 is equal to V4. Pressure 1, pressure 2. We know that the pressure 2 is double the pressure P1. Okay, find the ratio of the volumes of the gas. So we need to find V3 on V1. And we know that the work done by the gas, so basically it's the area of this is 200. So the area of this rectangle, area of rectangle is 200 joules. Okay, so that means that P2 minus P1, that's the height of the rectangle, times V3 minus V1, and that's equal to 200 joules. And P2 minus P1, well, P2 is 2P1, so 2P1 minus P1, that's P1. P1 times V3 minus V1 is equal to 200 joules. Well, instead of 200 joules, let's just call it A for now. Because I don't like mixing letters with numbers. A, this is A, this is A. Right, so we can write down A. Then we can say, all right, with the maximum temperature is here at T3, at 3, and the minimum temperature is at 1. So we can say that P2 V3 is equal to nRT3, and at 1, P1 V1 is equal to nRT1. In other words, P2 V3 minus P1 V1 is equal to nR T3 minus T1. Okay, And from here, I can say, but P2 is 2 times P1. So it's 2 P1 V3 minus P1 V1 equals NR delta T. Because delta T is known, delta T is 60 Kelvin. And we are left with P1. Do we need that? No, we don't. P1, 2 times P1 V3 minus P1 V1. Okay, we don't do anything to it. We'll leave it like this. And here we have P1 V3 minus P1 V1 is equal to A. And we put that into here. 2 times P1 V3. P1 V3 is A plus P1 V1. 2 A plus P1 V1 minus P1 V1 equals NR delta T. So in other words, 2A plus P1 V1 is equal to NR delta T. So here we can say that P1 V1 is equal to NR delta T minus 2A. And then we know this, P1 V3. This is the first thing. This is the second one. We substitute this into here, and we get 2 P1 V3 minus NR delta T plus 2A equals 2 NR delta T. And we have P1 V3 is equal to NR delta T minus A. I divided it by 2. Okay, 2, 2, 2. And divide by 2, P1 V3 is equal to NR delta T minus A. And from here, I can divide. So V P1 V3 over P1 V1 is equal to NR delta T minus A divided by NR delta T minus 2A. And P1 cancels out, and we're left with V3 V1. And the answer is approximately 3. Once you calculate it, it will be 3. So I don't know if you enjoy these kind of questions, because physics ends somewhere here. So it just comes down to writing equations and then solving them. And solving equations, by all means, is a skill. It's a very important skill. But yeah. Okay. The next one. The next one. I don't want to go too much through this one, but yeah. Let's say the work done by, find the work done by an ideal gas in the process 1, 2, 3, 1. So what do we need? Well, the work done in the process 1, 2. The work done in the process 1, 2 is the area of the trapezium. So this is P1, this is P2, this is V1, this is V2. The work done in process 1-2 is the area of the trapezium. So it's going to be, this is P3. P3. So it is P1 plus P2 over 2 times V2 minus V1. And the work done in the process 3-1 is negative. So it's negative P1 plus P3 over 2 times V2 minus V1. And the total work is equal to, well, V2 minus V1, as you can see, is a V2 minus V1. You can take it out, and you are left with 1/2 also takes out, and you are left with P1 plus P2 minus P1 minus P3. And so this cancels, and you are left with 1/2 V2 minus V1 multiplied by P2 minus P3. What happens next? Well, we need to see that, well, V2 minus V1. Okay, so what we know? We know that temperature T1, we know that T1 is equal to T3. And that means that P1 V1 is equal to P3 V3. But V3 is equal to V2, so it's equal to P3 V2. That's the first thing. P3 V2. And that means that V2 over V1 is equal to P1 over P3. This is the first piece of knowledge. And second piece of knowledge, that this is a straight line. That this is a straight line, so along this line, P is proportional to V. And that means that P1 to P2 is the same as V1 to V2. Okay. And also, and that means that P1 V1 over P2 V2, which is equal to nRT1 over nRT2, which is simply equal to T1 over T2. In other words, P1 over P2 is equal to V1 over V2, and it's equal to the square root of T1 over T2. Okay? So therefore, V2 is equal to square root of T2 over T1 times V1. That's the first piece of knowledge. That's another piece of information. And P2 is equal to square root T1 on T2, P1, and P3 is equal to V2 on V1. No, V1 on V2, P1, which is V1 on V2 is square root T1, T2, P1. Complicated. Okay, so very carefully, 1/2, so V2, so square root T2 on T1, V1 minus V1, P2, so that is square root T1 on T2, P1 minus square root of T2 on T1 Okay, where did I go wrong? Where did I go wrong? P3 is V1 on V2. Okay, and P2 is T2 on T1. Sorry, apologies. T2 on T1. So that's T2 on T1. This is T1 on T2. P1. Okay. So we can take out P and P1 and we can take out V1. So 1/2 P1 V1, open bracket, square root of T2 on T1 minus 1, multiplied by square root of T2 on T1 minus square root of T1 on T2. I don't think we need to do anything with that. And so P1 V1, we know that P1 V1 is NR T1, and T1 is known, so is N. So it is 1/2 NR T1 and that. So I don't know. I don't know if you enjoy these kinds of questions. I enjoy that from. I enjoy the fact that from something seemingly quite random, we can extrapolate. So just knowing T1 and T2, we can work out the work done. But yeah, I don't know. Any questions? Any questions? I think this is all for today from my side. And yeah, just I don't know if you received this message, but we are expanding. COMPOS is expanding. Next year we are we're taking on board year 10s, and because of that we'll need new tutors, and you guys can become tutors for COMPOS, not this year but the year after. When you're in second year of university, you can become a tutor for COMPOS. And this would be an amazing opportunity for us, of course, because we need tutors, and for you, because you've already studied this material, you can teach this material. You can make some extra money. So if you're interested in that, we'll be happy to see you back in a year's time, so in 2024. Right. Okay. So does that sound something you'd be interested in? Okay, we said COMPOS in year 10. You'd yeah, but you can have COMPOS in year 10. It just you'll be a tutor. Yeah. Okay. Yeah. must ask. Do you want to ask me something? Sorry. Well, yeah, as long as you study physics, yes. Yes, you can. You don't have to be an Oxford student for year 10. Yeah. As long as it's physics or physics and math course. Well, if we only had Oxford tutors, well, mostly we have Oxford tutors, like 95% with Oxford tutors, but we'll run out very quickly, especially when we add year 10s, and then we plan to add year 9s, year 11s as well. So, okay, so something to think about, and yeah. So, all right, see you next week, and enjoy the rain and horrible weather. See you.